Example 1. When a 2-gram sample of pure phenol is completely burned according to the below equation, 64.98 kilojoules of heat is released. Use the information in the table below to answer the following questions. A. Calculate the molar heat of combustion of phenol in kilojoules per mole at 25 degrees Celsius. B. Calculate the standard heat of formation of phenol. C. Calculate the value of the standard free energy change for the combustion of phenol. And finally, if the volume of the combustion chamber is 10 liters, calculate the final pressure in the container when the temperature is changed to 110 degrees Celsius. Assume no oxygen remains unreacted and that all products are gaseous. To calculate the molar heat of combustion, we need to convert the given heat release to the heat released per mole. So over here, this is what we were given, 64.98 kilojoules, and we had 2 grams. We have to convert grams to moles, so we go to the periodic table, and we find the molar mass of phenol, multiply them, and we get a negative 3,058 kilojoules per mole. We put the negative sign in there because heat is released. Calculate the standard heat of formation, delta H, of phenol. We have our equation here where we sum up the heats of formation of the products minus the reactants. So we're given the products, and we look in the table to find those values. We found this value, the heat of combustion, over here, and then we have X for the reactants, because that's what we're trying to find. This is for oxygen. It's an element, so delta H is 0. Carry out the math, and we get X, which is the standard heat of formation of phenol, is minus 161 kilojoules. Calculate the value of the standard free energy change for the combustion. First, calculate delta S naught. We use a similar equation to what we did for the heats of formation. And these terms here, those are the coefficients in the balanced reaction. We looked up their delta S naught in the chart we were provided, and we get delta S naught is minus 87.67 joules. Then we substitute this delta S and the delta H from the previous slide into the Gibbs free energy formula. Carry out the math, and we get delta G is minus 3,084 kilojoules. And again, be careful here. Make sure you convert Celsius to Kelvin. If the volume of the combustion chamber is 10 liters, calculate the final pressure in the container when the temperature is changed to 110 Celsius. Assume no oxygen remains unreacted and all the products are gaseous. First, find out how many moles of phenol were reacted. Well, we have 2 grams of phenol. We take the molar mass of phenol from the periodic table, do some addition there, and we get the moles. Then calculate the number of moles of produced gas based on the ratio of 9 moles of reactant gas for each mole of phenol. And this is from the reaction equation. All products assumed to be gaseous and all O2 and phenol consumed. And here's the moles. 9 moles of gas, 1 mole of phenol, and these are the moles of the final gas. Then use the ideal gas law to calculate the pressure. PV equals nRT. Divide both sides by V, and here's our number of moles. Here's the universal gas constant in the proper units for dealing with liters and atmosphere and moles. Here's Kelvin. Again, be sure to convert Celsius to Kelvin, and we get 0.601 atmospheres.